Okay, so welcome to another screencast. This one is characteristics of stars, and we're going to teach you how to read page 15 of the Earth Science Reference Table. So take out your handy dandy Earth Science Reference Table, turn to page 15, and page 15 looks like this. Part of page 15, I should say. I'm just going to start just by kind of looking at the title, Characteristics of Stars. It's also called the HR diagram, after Hertzberg-Russell diagram. There's a whole bunch of things to go over about it. If you look at the x-axis, it's describing surface temperature, and K means Kelvin. Notice there's no degrees because Kelvin doesn't have degrees, it's just Kelvin. At the origin, a little bit unusual, you'll see that it's 30,000 Kelvin, and as I move to the right, the numbers, temperature actually goes down. So I have 30,000, 20,000, 10,000, 8,000, 6,000, 4,000, 3,000, and finally 2,000 Kelvin. The other interesting thing about this is it also has colors of stars. So a blue star is hotter than a blue-white star, it's hotter than a white star, hotter than a yellow star, hotter than an orange star, and finally the coldest star is a red star. So the phrase red hot does not apply to stars. Blue hot would actually be the proper terminology. Now you compare surface temperature to luminosity, and luminosity, the units of luminosity, are comparing it to the sun. So the sun is the method of comparison for all the other stars that are on the characteristics of stars chart on page 15 in the Earth Science Reference Table. So if, for example, you noticed that a star had a temperature of 20,000 Kelvin and had a luminosity of 10,000, and if you put a dot where the two meet, that star would be in a category called the main sequence. Any star that falls within this range, all of these stars are considered main sequence stars. Stars spend about 90% of their life in a main sequence star, and as you can see, our sun is classified as a main sequence star. Represents the early stage of star development. We'll go over star development in class, but just think of it as the life cycle of a person, very similar. Intermediate stage, you have two options. If it's a very massive star, it could become a supergiant, and that would be the intermediate stage. So after early stage, it would graduate to a supergiant phase. Again, only massive stars will do that. Our sun will not be able to do that. It's not massive enough. So we'll never, ever, ever wear a cape, which is very upsetting, I guess. Then we have giants, which is what our sun will become, and that's the intermediate stage. It's about 4.5 billion years from now, our sun will go to this phase, somewhere around there, give or take a couple of million years. All right, so you can see a star like Polaris, which is the North Star, which is directly above the North Pole of our Earth, or in line with the North Pole of our Earth, is considered a giant star. Aldebaran, Pollux, are all considered giant stars. And then the last stage that our sun will experience will be a white dwarf. You might also say that a brown dwarf and then black dwarfs or something like that, eventually becoming a black dwarf. And this represents the late stage of star development. So Procyon b, which is also my rap name, by the way, when I do rap, is in the white dwarf phase. Our sun will eventually become a white dwarf. So let's take a little bit closer look at our sun on this chart. Kind of nice and easy is that its luminosity, you read across, would be 1. Its temperature would be, if you take a look, I'll take away the line again. You can see here 6,000, this is 4,000, therefore this line must be 5,000. So if you take a look, it's closer to 6,000 than to 5,000, so you can estimate it's about 5,700 Kelvin, and it's a main sequence star. If we looked at Sirius, and that's how you pronounce that, surely it can't be Sirius. I'm serious, and don't call me Shirley. We look to the left there, you can see its luminosity is between 10 and 100. It's closer to 10. Again, an estimate, fair estimate, might be about 30. Luminosity of 30, so it's 30 times more luminous than the sun. And its temperature is, and again I'll take that away, you can see it's in between 10 and 9,000, 9,500 Kelvin, somewhere around there. So that's how you read luminosity and temperature for specific stars or for star groups. Or if we give you the temperature and the luminosity, you should be able to tell us what type of star it is. Okay? So, let's kind of go back to our sun. The projected life cycle of our sun will be a main sequence star, which it currently is right now, and you can see in that amazingly beautiful handwriting, most of its life is spent as a main sequence star. It will then become a giant. After that, it will actually become a main sequence star again, and we'll talk more about that in class, and then eventually becoming a white dwarf. If you take a look at this development on the star chart, the characteristics of stars on page 15 in the Earth Science Reference Table, our sun, when it becomes a giant, what's going to happen? Well, if I take a look, here it is here in terms of temperature versus luminosity. As it becomes a giant, it's going to become colder. See how it's getting cooler? But what? More luminous. And that's because the sun is getting larger in size. There's more surface area for the heat to escape. Since it's a larger surface area, more light gets out and makes it appear to be more luminous, and it is more luminous. So our sun will do that, and then eventually it will run out of fuel. It will start to shrink again. As it shrinks, it gets smaller in size, becoming hotter because less heat can escape, and becoming less luminous, therefore making it more of a main sequence star again. Then eventually it will become a white dwarf. So it will keep shrinking and shrinking. It will shrink to about the size of Earth, and its luminosity will decrease, but its temperature will increase because it's less space for this heat to get out, and therefore become significantly hotter. Now, just a little point of clarification, which we'll talk about in class. This characteristics of stars page, these dots don't represent where they are in the solar system or where they are, but how they compare between their surface temperature and their luminosity. Very popular example is if you took the height and weight of people in the United States and you plotted your height versus your weight, you could have the same height and weight as somebody in California, and you might be next to each other dot-wise on that particular height-weight chart, but you're nowhere near each other geographically. So these stars, it's not showing their location in our galaxy, right, the Milky Way galaxy, but instead is just comparing them just on two factors, the factors of temperature and luminosity. And then you can also see over here, there are small stars and then there are massive stars. So over here, this gives you an idea of their size. So the brightest star on this page, Deneb. The least bright is Proxima Centauri. I mean, there are stars that are less luminous, but you can see Procyon b is pretty close too in terms of being really low on the luminosity scale. That's basically how you read this chart. And let's see, what should the magic word be? The magic word will be global. And you have to try and determine where exactly I came up with that in class, because it's within sight of my room, the word global.